All right, guys, let's look at our molarity slideshow. Hold on, what has happened here? There we go. All right, let's look at our molarity slideshow. So, in this lecture, we're going to talk about concentration, and we're going to work a couple problems that will kind of help us calculate the molarity of various solutions. Now, when we are looking at this, obviously we're looking at the concentration of a solution, and the word concentration and the word molarity are often used interchangeably. So, as we go through this, if you hear me doing that, don't be surprised. Now, some words that are really important as far as calculating molarity is concerned are words that we've already seen this year. So let's just refresh that a little bit. So solute is the substance that we're dissolving. Solvent is the substance that's doing the dissolving. Our solution is a uniform or a homogeneous mixture of a solute and a solvent. Concentrated means that we have a lot of solute compared to our solvent. Diluted is the opposite, right? It means we don't have a lot of solute compared to our solvent. We should be familiar with the term saturated, which means a solvent has all the solute it should be able to hold. We should be familiar with the term unsaturated, which means we can definitely get more solute to dissolve in our solvent. And supersaturated, which means we have more solute present in our solvent than we should. Now let's talk about molarity. What is molarity? Well, molarity gives us a way to quantitatively express concentration. All right, that's what molarity is. And it's defined as the number of moles of solute divided by the liters of solution. And so what we usually write is this: big M equals moles over liters. And if you know moles over liters, that's going to tell you how concentrated something is, and we call that the molarity. Now, when we're making Molar solutions, it really helps if you kind of visualize it with with this little drawing that we're going to do. So draw these 4 beakers. And in the first beaker, you're going to put 5 little dots. All right, so draw those. And I'm going to switch my pen color up here real quick. I'm going to black. So in the first one, we're going to go ahead and label this beaker A. We're going to say it is 1 molar. Now, in beaker 2, we want it to be in beaker B, we want it to be 2 molar. So how many dots would I need in order to double the concentration? That's the question that I have to answer that. Now, hopefully, this is pretty obvious, right? If we have 5 dots in the first one, and we notice that the level of solution is right there, the level of solution has not changed. So how many dots would I need now? When we had 5, we went 1 molar. So 2 molar is obviously 10 dots. Well, those should be in the circle. 10 dots. All right. Let's look at C. 0.2 molar. So again, we're comparing it to our first beaker, right? Beaker A. What is 20% of 1 molar? Well, if 5 dots gives me 1 molar, what's 20% of 5? Well, 1 dot. So we would only have 1 dot in the same amount of solution, right? Because again, the solution amount has not changed. Well, let's look at D. D is 0.4 molar. So how many dots would I have? Hopefully this one is, kind of jumping off the page at you, right? If 0.2 is 1, then we should have 2 dots here, okay? And that's what molarity is. It tells us how much solute, right, is in a given volume of our solution. Let's do a couple more. Make it a little more mathy. So if you look really carefully on this beaker, you can see that there is a 1 and a 2 right there. There's the 2, there's the 1. These are labeled. So the second line is a 1 liter line, and the second line, or the fourth line, sorry, is 2 liters. So I'm going to give you how many moles of solute are present. You're going to read the beaker and tell me the molarity. So we'll do the first one together, right? So what's the molarity here? Well, I have 1 mole of solute, and our water line is at 1 liter. So 1 mole divided by 1 liter is a 1 molar solution. All right. We're going to do 1 mole again, but notice the volume has changed. So this line is still 1 liter. That's still 2. So we're at half that. So we have 1 mole divided by 0.5 liters is going to be our molarity. So that's going to be 2 molar. All right. Let's look at G. 0.4 molar. Now take a minute. You do this one. 0.4 mole. What's the molarity? What's the molar concentration? So take a minute and see if you can figure it out. All right, I'm going to assume you did it. So the water level is up here at 2 liters. So I'm going to do 0.4 moles divided by 2 liters. And that's going to give me my molarity of 0.2 molar. That's going to be 1 dot. And that whole big sample there, we'd see 1 dot. All right, 2 moles. So my water level is at 1 liter. Hopefully we can do this in our head, right? 2 moles divided by 1 liter is 2 moles per liter. So that is 2 molar. All right, there we go. So that's the math. The math is not a complicated idea. It's just how much solute do you have? How much solution do you have? Divide moles by liters to get molarity. Now, what about if we want to change the solution concentration? Well, we've got 2 beakers here. Beaker on the left, again, has that 1 and 2, and we've got those 5 little dots. So we're going to say that solution A here is 0.5 moles of solute in 1 cubic decimeter. So what is the molarity? Well, remember, a cubic decimeter is the same thing as a liter. So I have 0.5 moles divided by 1 liter. Anything divided by 1 is itself. So obviously I have 0.5 molar solution. Now let's pretend we heat that beaker and we evaporate half of the solvent. So you can see we went from 1 down to 0.5 right there. So what is the molarity now? Well, it has to be 1. We didn't get rid of any solute, but we got rid of half the solvent. So we doubled the concentration, right? Let's see if that works out. We still have 0.5 moles because the solute didn't go anywhere, right? All we did was evaporate solvent. We now have half of the liters we started before. So 0.5 divided by 0.5 gives me 1 molar. So I have a 1 molar solution. All right, draw these 3 beakers. Okay, help yourself visualize it. So in beaker A, we've got 0.5 moles of solute in 1 cubic decimeter of solution. So 0.5 moles divided by 1 liter, what's the molarity? 0.5 molar. Okay, in B, we kind of got like a story going on here. 1 liter of a 1.5 molar solution was added to beaker A and the solution was stirred. So what's the new molarity? All right, well, if I have 1.5 molar of a 1 liter solution, how many moles do I have? Well, that should be pretty obvious. Anything divided by 1 is itself, so I must have 1.5 moles. So I started with 0.5. I've added 1.5. So 1.5 plus 0.5 is 2 moles. So I have 2 moles of solution. I started with 1 liter. I've added another liter, so that's 2 liters. 2 divided by 2 is a new concentration of 1 molar. There we go. Now let's say we take 0.1 moles of solute and we add it to that initial beaker, that beaker A, and we stir it. All right, well, this one's even easier, right? All it's talking about adding is solute. We're not changing the volume, right? We're still at 1 liter in both cases. So we say, all right, well, we had 0.5 moles. We added 0.1 moles. So that's going to be 0.6 moles. We still have 1 liter. Well, anything divided by 1 is itself, so it's a 0.6 molar solution. There we go. All right. Let's work a few more practice problems now. Let's look at a real practice problem. So it says, compute the molarity of the following solution. 5.23 grams of iron 2 nitrate in 100 milliliters of solution. Now, hopefully, this jumps right out at you and says, hey, wait a minute. That needs to be in liters, so I need to convert, all right, to liters. And I have grams, so I need to convert to what? Think about it. Yeah, moles, right? Because remember, molarity is moles over liters, right? We know the formula. Just plug in the right things. If you don't have the right things, you need to convert to get the right things. So we got to make sure we have moles and liters. So we know that molarity is moles of solute divided by our 1 liter solution. So we're going to convert 5.23 grams. I'm going to use the periodic table to get the mass of iron nitrate. It's about 180 grams per mole. And that gives me 0.0291 moles. There we go. 100 milliliters divided by 1,000 milliliters in 1 liter gives me 0.1 liters. And so take my formula, plug it in. 0.0291 divided by 0.1 liters. And I get a molarity of 0.291. There it is. That's easy math. That's basic math. We do our little conversions. We plug it into the formula. We're golden. All right. So I know you guys can do that. Let's look at one more. This one's a little tougher. This one's going to let us think a little bit. So I'm going to move my face up here out of the way so we can make sure we have something. So it says, calculate the molarity of each ion in a solution made of 193 grams of magnesium bromide in 5 times 10 to the 2 cubic centimeters of solution. Whew. Okay, we want molarity, so we know that. So we know we're going to need molarity is moles over liters. All right, we know we have grams, so we're going to need to convert grams to moles. And we know that in order to do that, we use the periodic table, right? The molar mass. We've got centimeters cubed. Hopefully you remember that 1 centimeter cubed is the same thing as a cc, which is the same thing as a milliliter. Those are all the same thing. So I need to convert I need to convert 5 times 10 to the 2 centimeter cubed to liters. I need to convert those things. So let's jump in and do that. Well, 193 grams of magnesium bromide times 1 mole over 184 grams gives me 1.05 moles of magnesium bromide. I take my 1.05 moles and I divide it by a half a liter, which that's what I have here. When I convert centimeters cubed to decimeters cubed, or it's a whole lot easier to just do milliliters. So let's do that real quick because I didn't show it, but I want to make sure that we walk through it. So 5.00 times 10 to the 2 milliliters, because I can just switch that over. 1,000 milliliters in 1 liter, and that will give me 0.5 liters. So that's how I got that number right there. One bracket conversion. So that tells me that I have a 2.1 molar magnesium bromide solution. And that's where most people stop and they get this problem wrong. Because the question says, find the molarity of each ion. So this is a problem that requires you to apply what you know about ionic compounds in solution. So in solution, magnesium bromide dissociates. It breaks apart. And it forms a magnesium plus 2 species. And it forms 2 Br minus 1 species, right? It breaks apart into its components. So that means, since I only have 1 magnesium, that's the molarity of magnesium bromide is going to be the same molarity as magnesium ions in the solution, right? It's a 1-to-1 ratio there. But the bromine is going to be double that because for every 1 magnesium ion, I have 2 bromine ions. So the actual answer here would be 2.1 molar magnesium and 4.2 molar bromine because it says, what's the molarity for each ion? That's a really common kind of question. So keep an eye out for that, all right? Make sure you don't make that mistake and stop too early. All right, let's apply this to how we would make a solution. Let's say I want to make 2.5 times 10 to the 2 milliliters of a 3 molar solution of cobalt chloride. I guess that would be cobalt 1 chloride. All right, well, how do I do that? Well, first, I need to get milliliters, all right, into liters. So I do 2.5 times 10 to the negative 2 divided by, right, I put my bracket here. Okay, there's my bracket. 1,000 milliliters on the bottom. That's going to give me my liter conversion. And I know that I'm going to be dividing that by molarity. And so I just put dividing that into moles to get molarity. So I just put the 3 moles on top. That second thing I need to do, all right, is I need to figure out how many moles to grams. Why do I need grams for this? Well, I'm describing a prep. So that means I need to be able to say, put this amount of COCl2 into this amount of water. That's what the problems mean when they say describe the preparation. I don't have a scale that measures moles, so I have to convert moles over into grams so I have something that I can measure. So the answer I get for this is 97.5 grams. So now let's take that answer and let's describe the preparation. And it's really simple, all right? Here would be the answer. Take 97.5 grams of COCl2 and add it to enough water, all right, to make 250 milliliters of solution. Now that's important, all right? You don't add it to 250 milliliters. You put it in your graduated cylinder and you add enough solution to bring the line up to 250 milliliters. Well, why is that? Like, why would I not just add it to 250 if it says 250? Well, remember, at the very beginning of the slideshow, it says that it's moles of solute divided by liters of solution, not liters of solvent. That's a very common mistake. And so if you want to ensure that you're very accurate when you are making your solutions, then we always make sure that we only add enough water to get up to the amount of total solution that's there. Now you might think, well, why can't you just add, what's the difference? Well, remember, matter takes up space, right? Matter has volume. And so that 97.5 grams of cobalt chloride is going to take up space in the graduated cylinder. A graduated cylinder measures volume. And when it's measuring the volume of the solution, it's not just the amount of liquid that you've put in, it's also impacted by the amount of solid that you're trying to dissolve. So you can't just add 250 milliliters. You add enough water to get it up to 250 milliliters. So describe the preparation one more time. You take 97.5 grams of cobalt chloride and you add enough water to it to bring the solution amount to 250 milliliters in our graduated cylinder. And again, 2.5 times 10 to the 2, we move that 2 places to the right. So that would be 250 milliliters, or I could just say 0.25 liters. That's where I'm getting that number. All right, so that's molarity. All right, if you have any questions, let me know. I'll be glad to give you a hand. All right, and I'll see you guys in the next video.